Good afternoon, everyone. We are a sense and avoid foreign entities in real-time drone, also known as a safer drone. At this point, I'd like to introduce our team.
Hi, my name is Jaspreet Singh. I'm the project manager and systems engineer of the team.
I'm Stephen Forte. I'm the hardware and electrical engineer for Nicholas Data Analytics and Software.
And I'm Kristen Contreras, and I'm your integration and test engineer. So to give you all an agenda for today, we will be reviewing our market pain, our originality of our project, our solution, which includes our standards, codes, and constraints, our best design, our system design, our final test phase, and the future for our senior design project. So, as you all know, drones are becoming more popular nowadays, so it is inevitable that the number of drone crashes and collisions will increase as time goes on. There are many obstacles in the outdoors for drones. These can be things such as trees, walls, buildings, airplanes, and other drones. As you can see to the right over here, in the recent news, there was a helicopter crash because it was trying to avoid a DJI Phantom drone. Because drones can fly as high as helicopters and are now even being used to deliver packages by Amazon, it is it is important that we implement a safer solution. So there are collision avoidance systems that do exist in the current market. To the left, you see the DJI Phantom 4 Pro that goes for about $1,500. So as you can see, that's very, very expensive. To the right, there is the DJI Guidance that goes for $1,000. The DJI Guidance has object sensing in 5 directions. Our safer solution can detect objects in 8 directions. So unlike those collision avoidance systems in the previous slide, our solution is both affordable and universal. We have used 8 ultrasonic sensors to detect objects in our environment. We use the Raspberry Pi microcontroller to process that information and to determine how to avoid objects. And we used S-bus communication for our communication between our flight controller and our Raspberry Pi. And we also designed a custom printed circuit board to integrate all our hardware components. So listed on our PowerPoint slide are the 3 main risks involved in our senior design project. Those are sensor inaccuracy, maximum drone stop distance, and hardware failure. In order to mitigate sensor inaccuracy, we used filtering to filter out erroneous sensor data. As for maximum drone stop distance, we conducted several tests and simulations to limit maximum speed to determine our threshold. And lastly, as for hardware failure, we maintained an existing fail-safe mechanism. So that means if the drone senses that there is hardware failure, it does fly back home. Moving on to standards, codes, and constraints, we did, as mentioned before, we used our S-bus protocol, which is also inverted UART. That is our digital serial communication. It is a single line that supports up to 16 servo motors, and it is supported by most flight controllers, including ours. And to the right, you can see our S-bus configuration. A single message has 25 bytes, and each byte consists of 1 start bit, 8 data bits, 1 parity bit, and 2 stop bits. As for our sensors, we use the HCSR04 ultrasonic sensors. That was for object detection and for outputting data to our Raspberry Pi microcontroller. Moving on to analyzing and testing to achieve our best design, general testing and debugging were carried out to connect our drone, sensors, and Raspberry Pi. Several flight tests were conducted to develop our MATLAB simulation, and we also did more trials to test our overall power consumption. We'd like to highlight, as shown in the figure below, that our standalone system does possess the same power capabilities as the drone itself.
Alright, so for our for our test and data analytics, so throughout our whole semester, we've gone through these test and data analytics to find out our system parameters. So as for drone metrics, as Kristen previously mentioned, we have a MATLAB simulation with the appropriate data obtained during flight tests. That was mainly used to understand the maximum speed that we can fly the drone at safely without it colliding into an object still. So the range of our ultrasonic sensors was around 400 centimeters. So from knowing that and knowing the deceleration of the drone from our initial flight tests, we determined that we can fly the drone at about 6.65 meters per second, which is about half the speed of the drone itself. Obviously, if we had more time, we can improve that further. Another test that we had to do was involving the S-bus signal communication data. So using the oscilloscope, we found out that it takes about 10 milliseconds for the Raspberry Pi to, for the remote controller to transmit the signal to the flight controller of the drone. We found out that 3 of those milliseconds is a signal actually sending, and then the 7 milliseconds is an actual lull in the signal, so we knew that we could actually send our S-bus signal from the Raspberry Pi during that 7 millisecond lull. And then finally with the flight tests, we failed flight tests a bunch of times, so we had to replace the ESC's electronic speed controllers and the motor connections. We had to replace them and resolder them in order for our system to work. So for the actual hardware design elements of our system, the ultrasonic sensor, the HCSR4 that Kristen previously mentioned, it has 4 pins. It has a power source pin, VCC, that connects to the Raspberry Pi. It has a ground pin also connected to the Raspberry Pi. The trigger and echo pins. So how the ultrasonic sensors ultimately work is that it has a trigger and echo. Trigger is the signal actually sent out from the sensor. The echo is the actual data coming back, determining how far away that object is, so we can use that in our system. The trigger pin goes directly right into the Raspberry Pi. And the echo pin, it actually works at a voltage of 5 volts, and we can't apply that to the Raspberry Pi because that would damage it, because the Raspberry Pi operates at 3.3 volts. So we just have to create a simple voltage divider, as you can see here, using a 1K and 2.2K resistor. So if we put a wire in between those 2 resistors, we have a voltage drop of 3.3 volts approximately across that 2.2K resistor. So the final circuit diagram, it looks big, but essentially it's just what I just showed you 8 times, because we have 8 ultrasonic sensors. So everything that's connected to the sensor goes to a GPIO pin in the Raspberry Pi, as you can see there. Yeah. This is our final PCB hardware design. So basically, the previous slide that I just showed you, that's basically it on the left, except that's the PCB board and we're actually designing it online. So as you can see in the middle, those are the GPIO pins connected to the Raspberry Pi, and the board itself makes the connections to the ultrasonic sensors, and it saves us a bunch of wires, and the system looks neater. So for the hardware design PCB process, the company that we use to actually customize the PCB board actually gave us a process overview on how the system was coming together. So it actually looked like it was done in one day, but they let us know when the drilling was done, when copper deposition was done, pattern plating, solder mask, silk screen, until the package was ultimately delivered to us. So again, more hardware design. So we found out early on that the flight controller can only read inverted UART signals from the remote controller, and that presented a problem to us because the Raspberry Pi can only send non-inverted UART signals. So a simple solution to this was that we just used this inverter that you can see here on the left. Basically, the signal coming from Raspberry Pi, we would put the S-bus signal into the inverter. The inverter would invert the signal, inverted UART, so the flight controller can read the signal coming from the Raspberry Pi. As you can see here on this circuit diagram, we sort of can't see. We have an inverter here. We're only using 6 of the pins. One of them goes to the receiver input of the drone. One of them goes to the receiving input of the Raspberry Pi. One of them goes to the transmitting port of the Raspberry Pi. One goes to the drone flight controller itself. And then the 2 extra pins are for power and ground. So cost per unit. So as Kristen mentioned before, there are avoidance collision systems on the market. But the goal of ours is to make it less expensive and affordable for amateur drone users. So as you can see here, the most expensive purchase was the Raspberry Pi. We already had one, but we have to factor it in if we wanted to design this in the marketplace. So the total cost came out to a little bit below $100. If we wanted to sell it at a market price of about 35%, so to say, then our selling price would be about $135, which again is way less expensive than the DJI Phantom guidance system, which is over $1,000. So that was the goal of our system, to create a less expensive option.
So here's some images of our hardware coming together. On the left side, you'll see the wires soldered directly to the PCB. Those wires then either go to the Raspberry Pi or to the flight controller. On the right, you'll see our lithium-ion battery is mounted directly to the PCB. It's connected to a interface board in the middle. That board allows us to provide the correct voltage and current to the Raspberry Pi, and then from the board, you have the USB connecting into the Raspberry Pi. So on the image on the left, we have an image of the flight controller itself. The wires top down are yellow, orange, and black. Yellow is ground, orange is 5 volts, and then black is the S-bus signal itself coming from the Raspberry Pi. In the middle, you see the Raspberry Pi mounted right above the PCB. All the wires are connected to the Raspberry Pi. Anything from the S-bus goes to Raspberry Pi, anything from the PCB goes to Raspberry Pi. And then finally on the right side, you'll see the connection from the receiver board that receives the commands directly from the user's controller. That also goes to Raspberry Pi. The wires are blue, orange, and yellow, blue being the S-bus signal, and then orange and yellow being the same as before. So here's an image of everything coming together. Again, we have the drone. Below it, we've mounted the PCB. Surrounding the PCB are the 8 ultrasonic sensors. Between the two, we have assembled all our hardware. So the Raspberry Pi is there, the lithium-ion battery is there, the inverter is there, and the interface board. So going over some of the software behavior. From start, the user will initiate flight. The remote controller then proceeds to send commands continuously to the receiver board on the drone. We intercept those commands and send them straight to the Raspberry Pi. Then we go in and obtain environmental data from the ultrasonic sensors. We ping them one at a time. The Raspberry Pi receives all this information and then determines whether or not an item is less than 50 centimeters away or greater than 50 centimeters away. And this is just an arbitrary number we use for our testing purposes. If it is less than 50 centimeters away, then we modify that S-bus signal accordingly to avoid said object. If not, we allow the user to continue manual control of the drone. If the user wishes to stop flight, they can, and the system will eventually come to a stop. If not, the cycle continues. So here's some sample of our code and results. On the top left is a sample function that we use to actually avoid objects to the front of the drone. What we do is we take the S-bus message and we split it up into a list of 25 elements. Elements 2 and 3 are associated with the front and back axes. So by modifying them to 64.0b, we cause the drone to fly away from whatever object's in front of it. And then we send that message back out to the drone. On the right, you see how we filter code. So we maintain a record of 15 sensor readings per sensor, and we have 8 sensors, so that's 15 by 8. For each sensor, we pass the most recent 16 readings actually to a filter, the Savitz Golay filter. The way the filter works, turbines we'll discuss later, but ultimately we take a window size of 5 elements at a time, and we use a quadratic polynomial to retrofit a smoother curve to filter out any noise. And then below that, you'll see how we actually measure the distance from the ultrasonic sensors. So we have stop time minus start time multiplied by a constant. And what we're doing is we're measuring from the time a message from an echo was sent out from the ultrasonic sensor to the time the echo was received once again. That is then multiplied by a constant, which is the speed of sound in centimeters per second divided by 2, so we get the one-way distance. And then on the bottom, we see roughly what our results look like. Each little bundle of information has the read value off the sensor, the filtered value, and then a series of 4 S-bus messages which are sent to the drone. So this is generally what we want our drone to do. If the drone is within 50 centimeters of danger and a user is trying to fly towards it, we interrupt that flight pattern and we fly in a modified direction. We also took into account if the drone was completely surrounded. So imagine that brick wall encompasses the drone within a 50 centimeter radius, then the drone is no longer allowed to fly in any of those directions. You can only fly up or down. So since the last time we discussed our project, we've had some scope changes. The biggest one being in vector analysis method that we were originally going to do. The new method is actually simpler, and we just modify that 25 byte S-bus message. So you see an example, we have 0F0004 and so forth. 0004 is associated with the left and right axis of the drone. So if you modify those values to say fly right when there's an object to the left of the drone, we are able to change specifically that axis and maintain any forward and backwards motion. So it's a combination of what the user wants and what we want the drone to do to avoid an object.
In order to mitigate the amount of errors inside the system, so taking out the noise inside the sensors, we're able to initially want to use filters, but the common filter that we originally wanted to use has some errors inside our system. The common filter is a linear quadratic estimate, which is able to optimize the sensor reading and produce accurate measurement based on previous measurements. So right now we're using the Savitsky-Golay filter, which is it has various data points, and from those data points it has adjacent values, and being able to convolve it, it's able to actually smooth out the data, and therefore filter out the outliers, and in order for us to have accurate sensor measurements. Testing, as we went over, initially we wanted to build a circuit. After building the circuit, we implemented the code, and finally we were able to test that. Using an indoor environment, we were able to actually have better sensor readings. So in order to fly in a bigger environment, we needed to have accurate measurements and ways to interact with the motors, ways to interact with the sensors and the flight controller. And here is a video of our drone actually working and not working. So as you can see from the first drone experiment, with a corrupted S-bus, the drone was not able to fly because it was receiving the wrong messages. By having a threshold of about 5 centimeters, we were able to have the drone able to detect the object in front of it instead of finding objects such as doors or walls or chairs inside that same environment. In test 2, the outdoor, we had the threshold adjustment. While the threshold was, if it's bigger than it originally is supposed to be, then it finds all the things inside the environment. Therefore, it's not able to actually function as it's supposed to function. And then for test 3, as you could see in test 3, we had not actually touched the controllers, and the drone was actually able to react exactly how we wanted it to react by using a 50 centimeter threshold. So our guarantee is that the drone will be able to stop in time before a collision, and having a inexpensive but also reliable system, we're able to do that. We had a Raspberry Pi. We used a Raspberry Pi, which is a very inexpensive system, $30, with a very fast microcontroller, and we use the ultrasonic sensor, very cheap also, and with accurate measurements. For a potential future for the safer drone, for building better sensor accuracy, instead of using ultrasonic sensor, which measures about 300 centimeters, we wanted to use a LiDAR sensor, which is able to detect a series of about from 0 to 120 meters, and actually implementing the common filter inside of our drone. Protective case for the drone, which protects the PCBs, the ESC, and other hardware inside the drone. To stabilize the flight from startup, instead of actually initializing the drone and it running away from you, we want the drone to actually be able to stand there and be able to take into functions. And finally, the system status indicator. When system is active, we want to be able to have the drone react and tell us where exactly the problem is. Right now we have the system where we have a stationary red light, but having a better system status indicator to actually tell us where the problem is, whether it's from the code, whether it's from the hardware or connection inside the Raspberry Pi, it would better help us for the overall benefit of the drone. And finally, the potential future for the safer drone, military, defense, mission applications, autonomous vehicle implementation, and also commercial use for amateur drone hobbyists. Thank you. Any questions?
Questions? Okay, thank